Let's do. I'll come into that momentarily. I want to share my screen. Let's start here on this one. Let's go ahead. And let me hit save. So now I know that there's probably more people trickling into our waiting room, so they're gonna have to wait until about 10:15, right? Idealistically, you wanna be waiting for me like at least 5 minutes before class starts, so that way when 10 o'clock hits, I do the best I can to start taking attendance right at 10 o'clock if that's when our class starts. So that's like being on time, right? And then once I'm done with the first wave of attendance, like taking attendance, I'll check it again at 10:15, right? Because the whole thing, because it's too much back and forth getting people as they come in with Starfish. Starfish is like not as user friendly as Blackboard, but you don't have to worry about that. Let's see, as far as announcements. I think this is week 7, right? So I think we have exam 2 next week, right? Yeah. So, okay. So that means a few things, right? So this is week 7. I think that's right. This week, we're going to be working on section 3.4, which is the last of the new material for exam 2. Exam 2 will be over chapter 3, so 3.1 through 3.4. Let me see. And you can anticipate pretty much a repeat of exam 1, just with different content, right? So it should become available, I think 7 days from right now, essentially. So next Wednesday at the start of class, it should become available, and then it's due the following Wednesday at the start of class. And again, like with all assignments, we get unlimited attempts at all assignments. The system is set to take our highest score, and we can work on any assignment past the due date with only a 10% late penalty. Okay. So let's see. Again, and as always, we kind of run the course in an asynchronous fashion. So what that means is that all I need from you guys on the day-to-day is at least get into my Zoom when we have our scheduled meetings. As long as you get into the Zoom and I don't stop you, that means you've gotten your attendance credit. You're not obligated to stay. But I do the best I can to try to fill that time like with relevant information, right? Until you guys like request. And again, the idea is that my intent was for class time to be basically like a study session or a Q&A, right? I just feel like lectures and homework because I feel like it's easier for everybody. And again, you guys can engage, you can unmute yourself, you can ask questions. We don't have to do what I'm doing. I just do it as a backbone structure. But if we want to do something else, or you guys want to do something else, we can. You can ask questions about anything too. You can even ask questions about exams, current exams, past exams, current quizzes, past quizzes, homework, etc. Anything that's on Pearson, you can ask me and we can talk about it. I may or may not like work it all the way out for you, but you don't know if you don't ask, right? I think I had a student last time. He said, "Hey, I think I got these questions right on my exam. Could you look at it?" I looked at it, and when I looked at it, by the time I was done, it took me a few minutes. It bumped his whole letter grade. It bumped his whole exam grade by a whole letter grade. I was like, wow. And I mean, because it was clear it was correct, he just typed it in wrong. And I don't think I gave him credit for everything, but I gave him what was just or whatever. But I can't think of anything else. Oh, and then right after a week, so this is week 7, exam 2 is during week 8. And then the week after that, we're going to spring break, right? So again, that's why I was talking about our class being remote asynchronous. So once that exam becomes available, if you're like all caught up and you get your exam where you want it to be, I mean, honestly, it's a remote class. So, you can start moving whenever you want. You just need to make sure to sit down at some point and make sure that your stuff in Pearson is in order. So like if you wanted to leave for spring break early, you totally can do it. Again, you just need to have a plan and execute. Make sure that you can access the internet, go ahead and get your assignment submitted, and then move on with your life. I don't expect you guys to be mathematicians. I don't expect you to sit with this and get as much joy and excitement as I do out of it. I'm not gonna lie. When I'm not with you guys, most of the time I'm gaming or figuring out how to game life. Because I really consider this life to be a simulation, i.e., a video game, and I consider myself the ultimate gamer. So one day I do fully intend to figure out how to hack the system. And I have a few. For instance, here's one hack that I recently came across as far as how this reality is a game. It's a little bit unorthodox, but someone did it. They did it for several years. They saved a whole bunch of money and they got free food, essentially. So it's a little bit unorthodox, but this guy did it. What this guy did, he bought a season pass at Six Flags. And what that does is that it allowed him free parking every time he went. And like, I think 2 or 3 meals a day, something like that. So he paid like $300 and got at least 2 meals for the entire year. That's a hack. That's a hack. Like, like that's genius. Like, and so he did that for a few years. And he saved all the money he normally would have been spending on money. He pocketed it, and like I think he paid off his debt and bought a house. But it took him a few years, but he did it. So if he could do it, and it makes perfect sense. And I thought about it for a hot second. So I mean, but it's stuff like that is what I like search for, right? You know, and there are others. That's just one of them. It's a whole bunch of them. But again, that's pattern recognition. To me, that's mathematics. He saw the pattern. He saw the opening. He had some critical thinking, and he took action. That is math. That's math, right? That's the kind of stuff that we're talking about. It's just that in these settings, they're very like linear and one-dimensional. It's numbers and symbols and communication, and it's very like disconnected, right? Because we don't relate, it's not relatable in that sense. But once you start to become clear about your passions and things that you love to do, and you take some of the concepts that we talk about here and apply them to what you love, then the realm of possibilities is endless, right? Okay, so enough of like the soapbox and hoorah and pep talk stuff. Let's get down to the nitty gritty and get into today's presentation. Let me see the time. We still got about, so what's that? 6 minutes before I check the attendance again. So, so today, I'm looking for my pen, is there? Let's go like this. So today, oh, okay. Sorry, I'm totally being, and again, all the stuff that you see me writing here on the screen, this is all available on our Blackboard page. I'm not gonna lie, I'm totally multitasking. I don't know if any of you guys play Dokkan Battle, Dragon Ball Z Dokkan Battle, but they have this new feature where it's like auto mode or whatever. So you start the thing and it automatically plays the match for you. I was like, yes, I can do other things and still grind. It's fantastic. I love it. It frees up my time. Okay, cool. So this is the last section of chapter 3. Exam 2 is going to be over all of chapter 3, and chapter 3 is about exponential and logarithmic functions. And so today, this is the official lecture for section 3.4, exponential and logarithmic equations and inequalities. A few objectives. We like to solve exponential equations. We like to solve applied problems involving exponential equations. We like to solve logarithmic equations. We like to use the logistic growth model, and we like to use logarithmic and exponential inequalities, okay? And again, if anything is not clear, just feel free to unmute yourself and stop me, get my attention, and we can pause for a moment and talk about it and do what we need to do. So in this example, we're asked to solve each equation, okay? All right, so these are exponential equations. There was a property we came across that says, basically the technique that we're gonna use here, we're gonna get the left-hand side and the right-hand side to be an exponential of the same base. Once we get them to be the same base, then we can just compare the exponents to solve the equation, right? So, for instance, in part A, we have 25 to the power of x, but 25 is the same as 5 squared. So this is going to be 5 squared to the power of x. 125, I think, is 5 to the power of 3, right? 5 times 5 times 5. So then when we say a power to another power, what do we do with those exponents? When we say a power to another power, what do we do with the exponents? We multiply those exponents, all right? So so the left-hand side is the same as 5 to the power of 2x. And the right-hand side stays as 5 to the power of 3. There's a property that says that these two exponential expressions are equal if and only if the exponents are equal. Right. So once we get these two exponential expressions to the same base, we just equate the exponents. And then divide both sides by 2, x equals 3/2, right? So we got this as our solution. Let me finish this equation. We're going to check it. I don't know if I shared this with you all or not, but I'm going to do it now anyway. And if I'm being repetitive, then you just have to bear with me. Come on. Come on. So we got this solution, right? And in math, whenever possible, you definitely want to check, right? So something like this, we can check it. I'm going to show you momentarily how to check it. But the ability to check questions before I submit them is how I was able to, is how I did well in my math classes and what got me far in math, right? Because like when I was doing my literature classes, I would do everything the professors would say. I would read the book, write the report, do everything. And then it just seems like they were giving me grades based on how they feel, no kind of like substance or anything. I'm like, yo, and it was always an argument. And it's like, you know, they had no real justification for the grade they gave me. And I used to hate that crap. I used to hate it, right? But in math, you know, if each step is justified, then you know whether the teacher liked you or not, it didn't matter. If it's right, they had to give you points, and I did that a whole bunch of times. Like even though the teachers didn't like me, they didn't have a choice because it was right, and I knew what I was talking about, right? And so, like for instance, when I was on exams, I would get this answer, and I knew how to check. I knew how to check myself. So let's try checking this. Let me see. Cancel. Let's do like this. Close the tab. So let's see how to check this one, right? So it was the ability to check my results. Like does you get an answer, you ask yourself, does this make sense in the context of the original? So if this is the answer, what that means is if we plug this into the original, it should make it true, right? So if we say 25 to the power of 3 by 2, we should get 125, and you see it there, right? So yeah, it was just I had too many, and that got me at least through undergrad and about halfway through grad school. Grad school was a whole nother thing because you had to create something new, and it was just a lot more intense, right? But at least that got me through undergrad. Let's go ahead and do part B, and I know it's about time to check attendance again. So again, the goal is with these exponential equations, we're trying to get the exponential expressions to have the same base, right? So with this one, we can bring down an equal sign. 9 is the same as what? 3 squared. So if we fast forward a little bit, the left-hand side is the same as 3 to the power of 2x. It's kind of the same logic as we did for part A. And then on the right-hand side, we have 3 to the power of x plus 1, right? So now that we got these two exponential expressions of the same base, now we just can compare the exponents. So this is going to be 2x. So the second line is true if and only if the exponents are equal, right? So then if we solve this, if we subtract x from both sides, we get what? X equals 1. Okay, so 9 to the power of 1 is 9. And then if x were 1, 1 plus 1 is 2. So then 3 squared is 9. So you can see that 1 works on the left. It makes the left-hand side equal to the right-hand side. So with that, let's pause for a moment. Let me check attendance. For some reason, my tablet is not like registering my touch. Let's see, let's go here. Let me stop sharing the screen. Let me go to participants. Oh yeah, we got a good amount. Let's go to edit.
I have a question.
Give me just a moment to finish attendance, and then we'll talk about it. Go ahead.
Okay, when you were doing the last problem, how did you get 2?
Clear the screen. Come on. This one. The 2. Oh, for part B?
Yeah, I meant 1. I meant 1.
Oh, the answer for 1? So
No, like I mean, like on part B, how did you get 1?
the final answer of 1?
Yes.
Yeah, so okay, here. Is this line okay?
Yes.
So once we got here, they had the same base. So then from here, we just set the exponents equal to each other, right? So that's what this came from, right? So then from here, all I did that I didn't show, I subtracted x on both sides. Minus x and basically minus x. So 2x minus 1x is 1x. Is that okay?
Yes, sir. I got you. Thank you.
Okay, so let's keep moving. Let me check one more time. Zoom. I think Zoom is good now. Okay, cool. Let's go on to the next one. And so I'll do the best I can to watch the clock. And this is just a typed version of what we just did. I'll do the best I can to watch the clock. Once time hits, like once class the time hits, I'll let you go if we're not done. But my intent is to, do this as one continuous stream. So I'll finish it. I'll probably let you guys go and I'll just go until I'm done. Solve for x, we have 5 times 2 to the power of x minus 3 equals 17. Okay, let me start by getting a copy. 5 times 2 to the power of x minus 3 equals 17. Okay. Solve for x. We want to use the inverse operation, right? We want to move things away from the x. So we're going to start with this 5. If we have 5 times this thing, we want to use the inverse operation, right? So the inverse of multiplication is divide both sides by 5. Okay. When we do this, a number divided by itself is 1. On the left-hand side, we're left with 2 to the power of x minus 3. And on the right, I'm just going to leave that at 17 over 5. Right? So now, in order to get our variable out of the exponent, we take the natural log on both sides, right? So if x is in the exponent, the opposite of exponential is log, or the inverse of exponential is log. So then we take the natural log on the left and the right. So you should notice a mirror image. What we do on one side, we do it on the other, okay? On the left-hand side, when we take the log, that allows us to bring this expression out of the exponent. And on the right-hand side, we're just gonna leave that as is. So if we bring down our equal sign, on the left, we're gonna have this x minus 3 times the natural log of 2. Side, I'm just gonna leave that as the natural log of 17 over 5. Okay. At this point, we just have some number, right? Whatever this number is, times x minus 3. So again, if we're still moving things away from our x and we're using the inverse operation, if we have some number times our parentheses, then the inverse of multiplication is division. So I'm going to divide, I'm going to undo the multiplication by dividing both sides by the natural log of 2. Right? Itself is 1. I'm going to keep working over here. left, at this point, we have x minus 3 equals, and on the right, we still have, notice I haven't crunched any numbers. It's okay to crunch the numbers early, but you just have to not round your answers. If you round your answers early, it's going to throw off your final answer. If you do crunch the numbers early, you have to write out the long decimal. So I prefer doing it this way because I don't really like writing out those long decimals. I feel like I'm more prone to make mistakes when I write out those long decimals. Natural log of 17 by 5 divided by the natural log of 2. And then there's only one more thing to move away from the x. All right, we're subtracting 3. So if we want to undo subtraction, the inverse of subtraction is addition. So we add 3 on both sides. Plus 3. Just a little bit. Sorry. A number plus its opposite adds up to 0. So now at this stage on the left, we're left with x. We've isolated our x. And then that's an exact expression on the right. And then we just put it in the calculator at that point to get an approximation. So you don't want to round until the very, very end. We're going to get the natural log of 17 over 5. Oh, that's not a 7. Come on. Over 5. And, you know, typing this in the calculator takes effort because you have to be cognizant of how you're using your parentheses and you have to use them correctly. Okay. You round to 3 decimal places. So we got, I'm going to say 766. So approximately. So once we start rounding, then it's not equal. We have to say it's approximate, which means it's close. Approximately 4.766. Okay, now actually before, let me see. Now, if we plug in this rounded answer into the original, we shouldn't get exactly 17. We should get something that's really close to 17. I can take that answer. Let's put in what we wrote, right? So to check, let's plug this into the original. We're going to say 5 times 2 to the power of, now the x, again, this is rounded, so it's going to be a little bit off. 4.766 of that minus 3. Then we should get something close to 17, right? Because we rounded. If we didn't round, then it would be on the money. 6. Type version of what we just did, they may have done something a little different, but I'm just going to compare the final results. 4.766. Here we're asked to solve the equation and approximate the answer to 3 decimals. Okay. Well, let's get a copy of the original. We have this 5 to the power of 2x minus 3. 3 to the power of x plus 1. This one, we can't get them to the same base, right? We don't have that luxury. So what we can do, if we're trying to, so we want to isolate our variable, we want to get the x by itself. So to get those x's out of the exponent, we take the, hopefully you're thinking it. Yeah, let's move over just a little bit. Both sides, right? That's what we did last time. So you'll find that a lot of these things, we're doing the same thing over and over, just in different order, in different ways, right? You kind of keep doing the same thing over and over in different ways. So now when we do this, this allows us to take these exponents out of these expressions out of the exponent. Okay, so then I think I'm gonna need some more space. So now at this point we have this 2x minus 3 times the natural log of 5 equals x plus 1 times the natural log of 3, right? That natural log of 5 and that natural log of 3, those are just numbers, right? We don't know exactly what those numbers are, you know, off the top of our head, but it's just a number. right? So you know how to handle numbers, right? You wouldn't be here if you didn't know. Should I say it to be a little bit more precise? So now again, we want to get the x by itself. So let's expand this out a little bit further. Let's expand this. So again, we have this binomial times some number equals another binomial times some number. So if we have this binomial times a number, let's expand it. Let's distribute. All right, let's distribute. We distribute that number. I think I'm gonna need to shift it over some more. Let's write it like this. Times the natural log of 5 minus 3 times the natural log of 5. Okay, we're okay. Equals x times the natural log of 3. Natural log of 3. I distributed this number into each set of parentheses. We can take each term that has x, any term that has x, we're going to get it on one side of the equal sign. And if that term does not have an x, it's going to go on the other, right? So I'm going to move my x's to the left and the other terms to the right. Okay, if I'm moving my x's to the left, that 2x natural log of 5, I'm just going to leave it. So we have this 2x natural log of 5. Now, if I want to move this x natural log of 3 to the left, if I want to move it, since that's positive, the inverse of positive or addition is subtracting. I'm adding a positive. So to undo it, I subtract it from both sides. So I'm going to say minus x natural log of 3 on both sides. Minus x times the natural log. Let's clean this up. 3, right? And then also I want to move that 3 natural log of 5 to the right. So the inverse of subtraction is addition. So I'm going to add 3 natural log of 5 on both sides. Add 3 natural log of 5 on both sides, right? So on the right, number plus its opposite as the 0. A number plus its opposite as the 0. Okay. Let's see, on the left, we're left with minus x natural log of 3. On the right, we have the natural log of 3 plus 3 times the natural log of 5. We're almost there. Each term on the left, they both have an x. Now we can, anybody know what this is called? Like, begins with an F. It's like reverse distributing. So distributing is where you like multiply and you expand it. The reverse of distributing, we want to factor out the x, right? So if we factor out an x from each of those terms, we're going to be left with 2 natural log of 5 minus the natural log of 3 equals the natural log of 3 plus 3 natural log of 5, right? So now at this age, we're like one move away. We have x times some number equals some other number. One more time. At this point, we have x times some number. This thing in the parentheses is just some number. It doesn't really matter, you don't have to know the number to know how to use the number, right? So we got x times some number equals some other number. So if we want to isolate the x, the inverse of multiplication is division. So we divide both sides by that number. Let me see, kind of out of space. Do this. Arrange this stuff momentarily. So we said we want to divide both sides by that number, right? So we're going to divide by this 2 natural log of 5 minus the natural log of 3. Divide by 2 natural log of 5 minus the natural log of 3, okay? A number divided by itself is 1, very zen. And then we get x equals whatever that is, right? So now at this stage, we just use the calculator to crunch. We kept it exact until the end, and then we round at the very end. Okay. So then let's see. Now I'm going to use my parentheses. I'm going to open up the top with the open set of parentheses. We have the natural log of 3 plus 3 natural log of 5. This closes the log, and this closes off the top or the numerator. I'm going to say divided by, and I'm going to do another set of parentheses for the denominator. 2 natural log, that's not natural log, 2 natural log of 5 minus the natural log of 3. We need to close off that log and close off the denominator. Okay, then it's set to run to 3 decimal places. So to the right of the 5 is a 3. That 3 tells us to basically stay at the 5. So then we get approximately 2.795. 2.795. Okay. All right. And then let me just kind of, I'm going to shrink all this down. I'm going to get it to fit on one page just because we can. Right there. Kind of want to move that as well. Give me just a moment. Let's move here, because I was just kind of running out of space when I was writing it. Let's put it here. Yeah. A little bit more space. So that goes there, and then we're going to put it back. And then we're just going to expand it as far as we can. Okay. All right. So then delete. And we left off here. Boom, like that. Yay. So like when I was chatting, this is why I was pausing, because I was trying to think of how to make it presentable. And I was like, well, let me just finish it and then I can rearrange stuff at the end. Man, I don't know about you guys. I know you're not writing, but maybe you are. I don't know what you're doing. But Lord, I am grateful for this iPad. Like no more being uncomfortable at the chalkboard, like dealing with chalk or markers or materials. All I got is power and internet. And, and I can do all the things I need to do. Is super clean, super clear. I love it. I love it. It makes my job so much easier. Like, and I get the whole thing about being in front of each other. I get it. But if you're serious about this, you don't need my physical body to be there. Like if you're serious, you don't need my physical body to be there. Because I'm going to say the same thing and present it the same way. And it's more than likely you feel the same way because my energy is intense. I've stopped trying to, I'll be as gentle as I can, but I know my energy is intense. So I don't resist it anymore. I just try to work with it and go from there. Okay, so we got this result and we can actually check this before we submit it. I know I'm kind of dragging, but it's okay. So let's check this. So now, if we plug this answer in, let me think about it. Because we rounded, it's going to be close, right? If we plug in this rounded result to the original, the left-hand side is going to be close to the right-hand side. So now, instead of doing it twice, like plug it into the left, you get an answer, plug it into the right, you get an answer. If these two are supposed to be equal and we subtract them from each other, something minus itself, it should subtract out to 0. So what I'm going to do is say the left-hand side minus the right-hand side, plug this in. And because we got an approximation, we should get something that's close to 0. Okay, let me show a technique to do this. So I'm going to go to my y equals, and I'm going to do 5 to the power of 2x minus 3. Close off the exponent, then I'm going to say minus 3 to the power of x plus 1. Home screen, call on that function. My battery is getting low. Let me charge this at least. Switch out my headphones, otherwise cut out when I don't want it to. I'm going to hit number 1. I'm going to hit 1 again. And again, when we plug this number in, we should get something that's close to 0. It might be a little bit more, it might be a little less, but it should be close to 0. 2.795, right? Close. I think you guys can still hear me okay. All right, it's charging. And so that was us doing it by hand with all the details. Okay. So then let's compare it. And we have typed up notes. You see the same thing, 2.795. So we did it by hand, and then you can see all the details from the prepared notes. Okay. So now I never took college algebra. I think when I was in high school, I took calculus, like AP calculus. And then when I went to college, I took calculus, right? So I kind of repeated the same course, but it just made for it. What they have, what that the effect of that cause was the cause for a smooth transition from smooth transition from high school to college for me. But on the other hand, what happened is there are some concepts in college algebra that you don't ever talk about in any other course, right? So I know, like, I don't know how you guys feel about being in college algebra too, but it's actually a blessing. Not, you may or may not go beyond, like, in as far much further in math, but at least you have a good foundation, because again, you guys are talking about stuff. I had to figure it out. A lot of this stuff, I didn't realize it until I went to teach it. I was like, oh, that's where that comes from. I had a professor in grad school was using something. I was like, what is that? What is he talking about? And I couldn't figure it out. Come to find out, it was in college algebra. I was like, oh man, I was so mad. But I mean, and I could have, figured it out, but it made it harder because I had no context. Like, I didn't understand where that was coming from. There was a reason I brought that up. But anyway. So we checked it. We got
Professor,
this
I have a
result.
question.
Go ahead.
Can you let Mason James in? He's been having problems with this connection.
It's no worries. I got him. Let's see.
And also another question I got in here later.
Yeah, as long as you got into my Zoom, then you've got attendance credit. So if they're still in the waiting room, then that means they haven't gotten it yet. So I'll get them now.
And also, I'm not sure if someone asked this already, but for 3.3, the quiz, some of the answers towards the end were like, I don't know, the estimate was weird. Like I got them right, but it said it was wrong.
Okay, let's look at it. For
3.3.
3.3?
Yes.
Let's see. Let me think about it. Okay, because I'm not sharing my screen. Let me pull it up. Let me think about it. Let me pull it up here first. Because, yeah, we're about to get out. And this is... Mr. Fisher?
Yes.
Okay. Let me look at it. So if I go here, 10 a.m. Gradebook. Yeah, and with that, while I pull up this document, let me see. Managed by students. The midterm grade will be basically based on everything from the beginning through exam 2. And again, the midterm grade doesn't bear any weight on your final grade. It's just a snapshot of where you are at that moment in time. All right. Let me see, Mr. You said this quiz. Was there anyone in particular one, like your highest one or the last one?
Yeah, I'll look. Hold on, give me 1 second. I think it was 4 and 5.
Oh, wait, 3, there's only one. Okay. So let's review.
What the heck?
Let's see, 5. If I look at 5, the half of the chemical round to the nearest integer. That was a rounding error. Because the nearest integer, you put 7.4. So
I just want it to be 7.
Yeah, because it says the instructions say round to the nearest integer.
That was the answer.
Yeah, and so you got it right, but you just didn't follow the instructions. So it's like, I don't know. Let me see. Let me look at this other one. Let me see. It says 4 decimal places. 1, 2, 3. So it was probably okay. And then for question number, that was also a rounding error. I'll give you credit for it because it's a quiz. On your question number 2, it says round to 4 decimal places. It says that you put 2.631, right?
It wanted me to like
I think
add a 0. Or
whatever was after that 9 was something that told you to stay at 9. So you should not have rounded at 9 up to the 10. It should have stayed at 9. I'll give you credit for it. Yeah, because that was a rounding error. The same thing with the last one. It's not right, but I'll just give you credit for it. It's not a big deal.
Thank you.
Mm-hmm. But I don't know, for exams that might be a little bit for a quiz. I don't mind.
I got you.
Exam, it might be a little bit harder. It's gonna be a little bit harder for me to do that.
I'll make sure I round better.
Yeah, it's okay. Submit the grade. Okay, so that's been changed. So I think you get credit for that. Okay, that timing was actually pretty good. Let me check the chat really quickly. I did for yours because you asked about it. We looked at it. It's okay. It's okay that you're late. Like, you made it in, you got your credit. It's all good. So, okay, so this serves as a good moment to like kind of release you guys. So again, this is the beginning of week 7. So again, next week we have exam 2 over chapter 3. And then the week after that is a spring break. We're remote asynchronous. As long as you're submitting your assignments, you can start your spring break whenever you feel like, at least as far as my class is concerned, you can start whenever. Just make sure that you get your assignment submitted and you're good to go. Again, your midterm grade will be based on everything from the beginning through exam 2. So once exam 2 is due, it'll be due the following Wednesday at the start of class. But again, that's going to be in the middle of spring break. But I'm gonna wait until the release is due. Then I'll check the grades and crunch midterm grades and stuff like that. Okay, if there aren't any burning questions, I'm going to release you guys, and I'm actually going to continue the stream. You're welcome to sit on if you like, or if you have the time or whatever. You can still engage, but I'm going to go ahead and at least finish out this section. Okay. All right, guys, take care. I will see you on Friday, same time, same place. And hopping back to our theory. Okay, let me see how far do we got. We got a ways to go, so I'm going to be here for a little while. But I want a clean stream, so far it's been pretty good. So I'm gonna keep going. Let me check one other thing. Yeah, let's keep going. And let me make sure. Okay, I think that's good to go. I'm gonna close this out. Okay. All right. So this one, we're asked to solve this equation. Okay. So let's take a look at it. Let me start by getting a copy of the original. So we have this 3 to the power of x minus 8 times 3 to the power of negative x equals 2. Okay. So I'm going to do a little bit of manipulation here. I'm just going to rearrange it so that we can use it. That 3 to the negative x, that's the same as the following, okay? I'm going to bring down that first term. Now 3 to the negative x is the same as three to the power of x to the power of negative 1. Because a power to another power, you multiply. So I just undid that technique, right? So then with this, we should be able to factor out that 3 to the x, right? Because we have two terms that have the 3 to the x. So then if we factor out the 3 to the x, we're going to be left with that first term is going to be 1 minus, now 1, it's going to be 8 times 1 to the power of -1 should still be 1. So that should be 1 minus 8. Is that okay? I think so. 1 minus this. Something feels off. Let me think about it. Let's undo that. Let's not do that. Let's back up because there's something doesn't feel right there. So I got another technique that we can do. Let's get rid of this one too. So that negative exponent, right? That's the one that's kind of like throwing me for a loop. That negative exponent, what does that mean? That means basically it goes to the denominator, right? So let's do that. So then we have this 3 to the power of x. That negative exponent means 8 over 3 to the power of x, right? Equals 2. So then one technique to get rid of your fractions, right? You can multiply the left and right side by the least common denominator of your denominator. So what I'm going to do, I'm going to multiply the left and the right by 3 to the power of x. All right, let's just do this and see what happens. Okay. Now on the left, when we distribute that guy, I don't know that this is the best way, but I'm just following the trail to see where it goes. 3 to the x times 3 to the x, what do? We add the exponent, so that becomes 3 to the power of 2x. The next one, they cancel, so that's going to be minus 8 equals, is this helping us? I think so. Let's keep going. And I'm going to leave the right-hand side as 2 times 3 to the x. All right, I'm going to leave those separate. So now I'm going to move the 8 to the right and move that other term. Actually, yeah. Dang. 3 to the x. I think, let's keep going. Let's move the 8 to the right, and that 2 times 3 to the x, let's move that to the left, all right? So if I add 8 on both sides and subtract the other one, we get 3 to the 2x minus 2 times 3 to the x equals 8, right? I added 8 and subtracted the thing. So now I got my 3 to the x's on one side. I think I'm one step away from being able to factor it out. Oh, okay. I see what's going on now. All right, so let's do this. I'm going to set it to 0. We have this 3 to the x squared, right? Minus 2 times 3 to the x, there it is, minus 8 equals 0. Yeah. So now we're going to use this technique called use substitution, right? It took me a little while to figure out. I was like, well, because at first I was trying to get it to equal exponents, but I couldn't get them to be equal. I was like, wait a minute, that's not working. Then I kept going, and then finally, now here I see that we can use this technique called use substitution. So what I mean by that, we're going to say, let u equal 3 to the power of x, right? So then if we do these substitutions, it's going to transform into something like the following: u squared minus 2u, and let's make those changes, u squared minus 2u minus 8 equals 0. So now we can factor it into a trinomial of something of this form. It should be u and u. Okay. Two numbers that multiply to give me -8 and add to give me -2. Because this guy here is negative, that means we need a positive and a negative. And then this first one tells us that the larger number is negative. I'm thinking 4 and 2. So a -4 and a +2. Let's just do a quick check. -4 times +2 is -8. -4 plus -2 is -2. Okay. So now we have two or more things that multiply to give us 0. So now we can apply the 0 factor property. When two or more things multiply to give you 0, either basically just set each thing to 0 and solve. So then if you set each product to 0 and solve, ultimately you're going to get u equals -2 or u equals 4, right? But then we need to go back and substitute our u back. So then that means 3 to the x equals -2 or 3 to the x equals 4. So take the natural log on both sides and divide. X equals, let me see. Okay, so for this first one, if we take the natural log, we can't take the natural log of -2, right? So this one, I'm going to just X this one out because I'm going to say this one has no solution, right? Because we can't take the log of negatives. But on the right-hand side, on the one on the right, if we take the natural log on both sides, we're going to get X equals the natural log of 4 divided by the natural log of 3. And then we use a calculator to get an approximation. That was an adventure. I'm an adventurer, by the way, if you hadn't noticed, right? I'm always using phrases like adventure. While I do these streams on the TV, I put on just like nature scenes, right? That's what I got, looping or whatever. And to me, it just lightens everything. It just makes the journey much easier than something feeling like a chore. If it's a chore, then I more than likely won't do it. So then we get one answer in 262, right? I'm just rounding to 3 decimal places. So we get approximately 1.262, okay? And what I'm going to do is shrink just this down. That's the only thing I was trying to get to fit, actually. Okay. And let's check this before we go forward, since we can. So, okay, so clear. So again, because it's an approximation, our final answer is going to be something close to 2. It should be. If I go to y equals, and I'm going to type 3 to the power of x minus 8 times 3 to the power of -x. And let's put that -x in parentheses. Okay. So then I'm going to go back to the home screen. I'm going to hit variables. I'm going to go to the right to go to y variables. I'm going to hit number 1 for function. Number 1 again to call in the function I just typed. And we're going to submit this result 1.262. We should get something close to 2. Okay. All right. So let's get rid of this. And we're going to compare this. Let's see how did the book do it. So now that negative exponent, okay. So yeah, they basically distribute. They did the same thing, right? They multiplied by the LCD. So they did multiply the left and the right by 3 to the power of x. You see the 3 to the 2x. It became 3 to the 0, which was just the 8, and then they get this. And then at this point, you can use the technique of U substitution. They let it be Y, but I called it U. It's the same thing. Okay. So then I think it's essentially the same thing, right? Where they called it Y, I called it U, but we did the same thing. Okay. Man, we got a ways to go. 262, you see it there. All right, let's give this one a go. So it says the following table shows the approximate population and annual growth rate of the United States and Pakistan in 2010, or Pakistan. Let me see something. Hey Siri, how do you say Pakistan? Oh my God. Hey Siri, stop. She was like saying all the languages in existence. It's like, Siri, just say the word. Hey Siri, how do you say this word? Pakistan.
Sending to Charles's iPhone.
Just say the word. Jeez. I just want to hear it.
Pakistan or Pakistan.
Pakistan. That's interesting. I thought it was gonna say something different. Gravity X prototype car. Oh my goodness. YouTube is fantastic. Okay. So we have these tables, approximate population, annual growth rates for the US and Pakistan in 2010. Okay, that's fine. So use the alternate population model that you see, where P naught is the initial population and T is the time in years since 2010. Assume that the growth rate for each country stays the same. Let me see, since 2010. Okay. A, estimate the population of each country in 2010. Okay. And what year will the population of the United States will be this? And what year will the population of Pakistan be the same as the population of the US? In 2010, let me see. In 2010. So the population, why is it not just that? Oh, in 2020, okay. So 10 years later. So we have this model, right? So basically they're asking us to estimate the population 10 years later, but the initial, so we're gonna let 2010 be year 0. You basically just plug these into the model. So for instance, if you were doing US, the initial population will be 308 million, so you just put 308. The rate, you will put 0.009, and the time will be 10 years. Let me see, I guess we can do that quickly. So in 10 years, let me see, can we, here, let's do this. Let's go to y equals. And the first equation will be for the US, all right? So the initial population was 308. Let's clear this out. 308, parentheses, 1 plus, the rate was 0.009, because it was 0.9%. You have to convert it to a decimal. And then we're going to say to the power of X, right? We probably didn't need to do all this, but this is fine. And then for the second one, that'll be for Pakistan, 185, parentheses, 1 plus 0.021 to the power of X. That's not X. Okay. So now I think for both of them, X is 10 years. So I'm going to call on each function. First, I'm going to call on the one for US and let the time be 10 years. And then I'm going to go ahead and call on the second function for Pakistan and also evaluate that one at 10 years. Okay. So then for part A, 336.87 million approximately. You see it here. Again, they just plugged in. They did the same thing we did. Plugged in. Oh, wait a minute. Yeah, this is fine, right? And then the second one, we got 227.73 million, right? And so you have a type version here of what we just did. And you saw us just do it. Solve for T. So when will the US be 350 million? So we set the final amount of 350 and we're solving for T. All right, so I'm just going to piggyback off of this. So then if we want to solve for T, we want to isolate the T, so we want to move things away from it. So to move this 308, we divide both sides by 308, and that's where this comes from. And then to get this out of the exponent, you take the natural log on both sides. So you're going to have the natural log of this, you see it here. Once you take the natural log on the right, the T comes down, you see it here. Well, actually you see it here, right? So that brings the T down. So then to get T by itself, we have T times this number. So then to isolate the T, we divide both sides by this number. So then T equals this, which you see it, this divided by that number. You get this. And then for these two to be equal, you basically set the model for each one equal to each other. And you know, you get something like this. Let's see. They got the expressions that have t on one side, so they divided both sides by 185, and they also divided both sides by this 1.009. And then because you're dividing, they have the same exponent, you can combine them like this. This stays as is. To get this out of the power, you take the natural log on both sides. You get this. The t comes down in front. You see it here. Divide both sides by this number, and then you get this, right? Man, we're only like halfway through the slides. I'm totally like burnt. All right, so now we have this one on solving logarithmic equations. Equations that contain terms of the form log base a of x are called logarithmic equations. So these are examples of log equations. To solve a logarithmic equation, we write it in the equivalent exponential form. So what we're going to be doing, with a good amount of these, we're going to be rewriting the logs as an exponential, right? So again, to do that, to change this log to the exponential form, you take the base of the log, you swing it to the other side, and it becomes the base of the exponent. Okay. So let's give this one a go. Oof. So we want to solve this. So let's isolate the log first. Let's get the log by itself. So if we subtract 4 on both sides, we get 3 log base 2 of x equals, what is that, a -3. I want to say this has no solution, because if we isolate the log, right, if we divide both sides by 3, we're going to get log base 2 of x equals -1. But oh no, the log, yeah, we can do, let me think about it, 2 to the power -1. Yeah, we're okay. Let's keep going. So we divided both sides by 3, we get this. Now we're going to rewrite this log in its equivalent exponential form. So this base 2 is going to swing to the right and become the base of the exponent. So then we're going to get x equals 2 to the power of -1, which is 0.5. Okay. And suppose we want to check this in a calculator, right? So let's see. We need to capture that change of base. I'm going to go to my y equals and check it there. So I'm going to say 4 plus 3 log of x. Now to capture that base 2, we need to say divided by the log of 2. Okay. So then I'm going to call in that function that we just typed in, and we're going to put in 1/2. And we should get exactly 1. Okay. And we checked it. We plugged it into the original. Solve. Okay. I'm going to start by getting a copy of the original. So we have this log base 4 of x plus log base 4 of x plus 1 equals log base 4 of x minus 1 plus log base 4 of 6, right? So let me think about it. Okay, so I think we had these 3 properties, these rules for logs. The log of the product is the sum of the logs. The log of the quotient is the difference of the log. The log of the power is the power times the log. So we can take those properties and actually use them in reverse. Let's see. On the left, we have the sum of the logs that have the same base. So we can condense that into log base 4 of x times x plus 1. Right? Something similar on the right, log base 4 of 6 times x minus 1. Okay. So then Let me think. We can either rewrite them as an exponential, or I want to say that these are true if and only if you set each of those terms equal to each other, like this. X times x plus 1 equals 6 times x minus 1. So then I'm going to expand and isolate my x's, right? So if we expand this out, we'll get x squared plus x. I'm going to go ahead and subtract the right from the left. So it's going to be minus 6x plus 6 equals 0. So then we have x squared. 1 minus 6 is negative 5x plus 6 equals 0. So then at this point, we have a trinomial. So we should be able to factor it. They should be the same, and they should both be negative, the signs. I think it's 3 and 2. Notice that negative 3 times negative 2 is a positive 6. Negative 2 plus negative 3 is a negative 5. Okay. I just got to continue here for now. So if you set each product to 0 and solve, we get x equals 2 and 3. We need to check these in the original, because sometimes what happens is we produce what I call the right wrong answer. Algebraically, it's correct, but sometimes they actually don't work in the context of the original because they're outside the domain. Right? Sometimes that happens. So whenever possible, you want to check. Lord knows whenever possible, I want to check. give me a check. I'm totally sleeping. I want to go to sleep. Okay. So let's check this 2 and the 3. Oh, let's see, that's a lot. I'm gonna piggyback. Okay, we can do it. It's gonna be a good amount of typing, but we can do it. And again, if the left is equal to the right, if we say the left minus the right, the result should be 0. So I'm gonna go to my y equals. I'm gonna do my log of x divided by the log of 4 plus the log of x plus 1 divided by the log of 4 minus the log of x minus 1 divided by the log of 4 minus, because again, I'm setting this equal to 0, log of 6 divided by the log of 4. So these are the change in base formula, right? So I'm going to quit this. I want to call on that function that I just typed in. When x is 2, we should get 0. And when x is 3, we should get 0. Okay. So we got 2 and 3. They seem like they worked. And here's a type version of what we did. So they checked the 2. Yeah, we did both of these. Okay. So I think what we said, the log of the product is the same as the sum of the logs. So these are a couple more examples where we're working those properties in reverse. So for part A, if we condense that, we're going to get log base 2. We're going to have this x minus 3 times x minus 4 equals 1. We can write this log as an exponential if we swing the base of the log to the right. Oops. So then that gives us, I'm going to go ahead and expand that. So we get x squared minus 4 minus 3 is minus 7x plus 12, 2 to the power of 1. So I'm going to say minus 2 equals 0. So on the right-hand side, I actually had 2 to the power of 1, but I went on to subtract it from both sides. So then we get x squared minus 7x. 12 minus 2 is plus 10 equals 0. So then we should be able to factor this. Into something of this form, x and x, minus and minus, 5 and 2. So then x equals 2 and 5. For part A. And again, we need to check. Let me go ahead and do part B, and I'll just check them simultaneously. So then for part B, I think we could do something similar. We can condense that. We'll get log base 2. Log base 2 of, I'm going to end, oh, we divide, okay. So we're going to have x plus 4 over x plus 3 equals 1. So then we can write this as the equivalent exponential. So then we're going to get x plus 4 over x plus 3 equals 2. I'm going to multiply both sides by the denominator and expand. We have x plus 4 equals 2x plus 6. I'm going to subtract x and subtract the 6. Ultimately, you get x equals 4 minus 6 is negative 2. And again, we let's check this in the context of the original. Okay. So I'm gonna go to my y equals. For part A, log of x minus 3 divided by the log of 2 plus log of x minus 4 divided by the log of 2. Okay. And let me go ahead and do the second one. Type this one to type it in. The log of x plus 4. Oh man. Oh, yeah. Log of x plus 4 divided by the log of 2 minus the log of x plus 3 divided by the log of 2. Okay. All right. So now let's go back. Variables. Now when we call in that first function, if we plug in x equals 2, we should get an answer of 1. Okay, so I think the 2 so it looks like the 2 produces a non-real answer in part A, right? So if we try to plug in 2 into the original, 2 minus 3 is negative 1, so that produces a non-real answer, so it can't be 2. Let's try 5. Let's quit. So 2 can't be 1. Let's try 5. When x is 5, we should get 1. So that 2 is what I like to call a right-wrong answer. Algebraically, I think it's okay. But then when you check it in the context of the original, it didn't work, which means the 2 is outside the domain. So it's just the x equals 5. And then for part B, let's try when x is negative 2. We should get an answer of 1. So I'm going to call on that function. And now we're in slot number 2. Again, we were saying when x was -2, so y of -2. We got our desired 1. Okay. If we didn't check it, we would have gotten that one wrong, right? Algebraically, the 2 was fine, but it was outside the domain of the original, so then we couldn't use it. So you see the 2 and the 5 at the bottom, but then if you check the 2, logarithms are not defined for negative numbers, so 2 is not a solution. If you check the 5, you get something true, so the solution set is 5. Part B, did we miss something? Was that a plus? Was that a typo? Because we have a minus. I think there's a typo. Yeah, we definitely had a minus. Okay. Well, I'm gonna let ours stand. I'm just gonna note that this was a typo right here. This is a typo. Okay. I'm gonna let it be for now. Actually, let's cut. Okay. I'm just gonna let that -2. I'm just gonna let that be for now. Okay. Suppose the carrying capacity M of the human population on Earth is 35 billion. In 1987, the world population was about 5 billion. Use a logistic growth model of P.F. Verhulst to calculate the average rate K of growth in the population, given that the population was about 6 billion in 2003. So we're using this model. It says that M is 35 billion. In 1987, the world was about 5 billion. So if that's our year 0, so when the time is 0, we would have 5 as the answer. So that would allow us to solve for A. So if we let, for instance, if we let the time be 0, which is the year 1987, the population of humans on Earth was approximately 5 billion. Carrying capacity M is 35. So they plugged it into their model. This collapses to 0. E to the 0 is 1. So then we get this. So then we get this equals 5. So multiply both sides by this denominator. You see it here. They divided both sides by 5. Long story you get was A equals 6. So then they take that and plug it back into the model, and we wanted to solve for K. And the time has been so they were solving for K. I think they keep doing typos. Right here, I think that's supposed to be a K and not a T. All of these are supposed to be Ks. All right, and they eventually put the K in the end, but you get this. Okay, summary. Okay, I think this is the last one. I think I'm spent. I have no more energy. I'm about to fall asleep. Let me give it a go. So solve, let's see. So we can subtract 3 on both sides. If I bring down my inequality, if we subtract 3, that gives us 15 on the right. And then on the left, we have this 5 times 0.7 to the power of x. Okay. Divide both sides by 5. 0.7 to the power of x is 3. Okay, if we take the natural log on both sides, on the left, we're going to have x times the natural log of 0.7. It's less than the natural log of 3. I want to say, okay, so the natural log of 0.7 is a negative number, right? It's between 0 and 1, so that number is negative. So when we divide, the inequality should flip. So then we're going to have x is greater than the natural log of 3 divided by the natural log of 0.7. So it has a hidden negative that we had to be aware of. And then I would just use my calculator from that point to crunch the number. So x should be greater than that number. Yeah, right. So you see those changes there. All right, let's give this one a go. Let's do the same thing. So we can write this one as an exponential. This is log base 10. So we just swing the base over. We're going to have 2x minus 5 is less than 10. Add 5. I think this is okay. I'm trying to think. Add 5, we get 15. $7.5. Okay. I'm just going to check undo. I'm just going to use my prepared notes to check this. Now, if we wanted to check it ourselves, we could like keep choosing points. We can choose several points that are in our system in the solution set to make sure that they work. All right. So for instance, if we chose the number 7 and plug it into the original, we should get something that's less than 1. If we choose anything that's less than or equal to 7.5 and plug into the original, we should get answers that are less than or equal to 1. We got x is less than. Oh, that's for the domain. That's fine. So 7.5, x is less than this. Combining, so we should have identified our domain. X is less than that, but it has to be greater than 5/2. So we should do, that is something I missed. We should have identified the domain first, right? And so for the domain of a log, because we can't take the log of negative numbers, this part has to be actually, this 2x minus 5 has to be strictly greater than 0, right? And then when you solve that, you get this. This is a solution set that we got. When you combine these together, this combined with this gives us this result here. Okay, that was interesting. And on that note, we're going to end the session here, right? So that brought us to the end of chapter 3. So we're now ready for exam 2 over chapter 3, and that exam will be available this upcoming Wednesday, start of class, all right? If there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Okay, take care, guys. Peace.